So to continue our discussion, we said the clam time series was produced, and then came Beatrice Arellano Nava of University of Exeter to interpret things, and obviously she's focused on tipping points. Some people are obsessed about it, and most of them are in Europe, as I've mentioned elsewhere. US doesn't pay much attention to this. Actually, the rest of the world doesn't either, because people tend to get carried away sometimes with some things. A tipping element in the Earth's climate, experts often say, is like a person leaning back in a four-legged chair. As long as it isn't pushed too far, the system can quickly recover from disturbances and return to its original stable state, but as it tilts toward its tipping point, the system becomes wobbly. Its variations get bigger and last longer, and this lack of resilience is thought to be an early warning signal of a tipping element nearing collapse. So you jump to a new state. I've discussed the tipping point and my issues with it elsewhere already, but this is a different context anyways. Perhaps Arellano Nava thought the clams might have captured this kind of signal in the years leading up to the Little Ice Age, which spanned from roughly 1300 to 1800, and if scientists could identify the warning signs that preceded the Atlantic's sudden cold snap more than 700 years ago, it might help them understand what is happening to the AMOC today. So if you go from medieval warming into the Little Ice Age, the Greenland became uninhabitable for the Vikings. There was volcanoes that may have initiated some cooling. Then you have sunspot minima that also reduced the energy coming in, and then came this sudden shift. And that's the claim, but was there evidence for it? Warning signs. In the year 649, paper money was a hot new invention. Visigoths controlled Spain and Portugal, and a young clam was beginning its life near the Icelandic island of Grimsey. This is a dramatic writing, right? The bivalve was born at an opportune time, just before a natural increase in solar radiation and decline in volcanic activity that contributed to higher temperatures in the northern Atlantic. As the clam aged, it enjoyed longer growing seasons and increasingly abundant food, allowing it to add ever thicker annual lines to its shells. So the data of the clam annual bands is being interpreted in a nice way. The prime conditions also had a chemical effect on the clam. Warm ocean waters tends to contain more of a lighter form of oxygen known as the oxygen 16. Oxygen we think about as 16, 17, 18 isotopes, and what gets taken up depends on availability and energy, while colder waters are disproportionately laden with the heavier atom called oxygen 18. Relatively large amounts of oxygen 16 in the clamshell attest to the balmy seas surrounding it. Why this fractionation happens, I've discussed elsewhere in detail. Basically, when it evaporates, lighter waters goes out more. When it precipitates, heavier water falls first. So H2O16, H2O18, and what remains in the ocean is related to what is happening with the evaporation and precipitation. If you keep growing glaciers, what happens, and so on. By the time this clam, the oldest in Reynolds' chronology, died in the year 988, the northern hemisphere was near the peak of a warm period known as the medieval climate optimum. The Vikings had ventured all the way to Greenland, and The Vikings had ventured all the way to Greenland, and England was temperate enough to grow grapes of wine, which is getting there again. But change was on the horizon. Around 1180, several clams living near Grimsey began to record strange shifts. Stretches of poor growing conditions were more frequent and longer lasting. The ratio of oxygen 16 to O18 started to fluctuate, hinting at an ocean climate that was oscillating between extremes. You can tell it's losing stability, Arellano Nava said. The environment is really struggling to maintain equilibrium. Other material from the bottom of the ocean, including bits of debris that were originally part of Greenland, suggests that chunks of glacier ice were falling into the ocean around this time. This would have diluted the salt water of the AMOC, causing it to weaken and creating a the fluctuations that got recorded by the clams. By the way, there is also volcanic activity that started to pick up in the 12th century, and there are some arguments made that the current cooling around the southern tip of Greenland is not only AMOC signal but also maybe volcanic signal. So you have to be careful when we interpret. You get some evidence from the past and you start to interpret it based on multiple data. It's like a detective work, and it's very interesting and important, and yet there can be uncertainties, right? The initial volatility subsided toward the end of the 13th century, but it returned with a vengeance around 1330. First came wild fluctuations in the clamshell's oxygen ratios, then indicators of temperature took a nosedive. The growth lines in the shells became thinner as colder conditions depleted the clams' food supply. Above the surface, humans were also struggling to survive. Historical records from northern Europe document harsh winters and brutal famines as regional temperatures fell by 1 to 2 degrees Celsius. Meanwhile, tropical regions saw major shifts in rainfall patterns, disrupting societies from India to the Amazon. So we know when high latitudes begin to cool how the rain band or the intertropical convergence zone shifts, and those records also remain in many proxies like in the caves and so on. Scientists debate what exactly caused the Little Ice Age. Changes in solar radiation, volcanic activity, and the reforestation of North America following the decimation of Native American population have all been blamed, and they could all be potential contributors. Yet the first unstable episode in the shell record preceded those potential causes, suggesting that the ocean played a critical role, Ariano Nava said. Well, that's still an interpretation, because it's possible that the ocean was doing something. These additional perturbations pushed the system over, right? So ocean wasn't able to do it by itself, even though it was moving in that direction. Because the changes were concentrated in the North Atlantic, the AMOC couldn't have completely broken down, she explained, but there did seem to be an abrupt downturn in a crucial component of the system known as the subpolar gyre that prevented warm water from flowing to the clam's seafloor home. Frigid Arctic currents filled the void, helping to trigger a regional cold snap. Meanwhile, solar and volcanic factors likely contributed to and amplified the change. So as I said before, you have the upstream branch in the subtropics, which is bringing warm waters, and you have a downstream branch which is taking heat out into the Arctic. So where you perturb the system can depend on many details. Tim Lenton, that I mentioned before, who directs the Global Systems Institute at the University of Exeter and contributed to the Little Ice Age study, called a subpolar gyre downturn the little brother of an AMOC collapse. So Tim Lenton is a huge fan of tipping points, and he has written a book, edited version of a book as well, and so on. The AMOC could step down in strength without completely collapsing, Lenton said, and the impacts could hit you quite quickly. So that's where he begins to get more and more vocal, and that's his style. What's more, Ariano Nava said the clam records show there were warning signs of the coming transition, though no human knew it at the time. The fluctuating growth lines and shifting chemical compositions are indicators of the gyre critically slowing down, the wobbles of someone tilting back in a chair just before they tip over and fall. So what is the future? It's uncertain. An uncertain future, to scholars of Earth's climate, the clamshells and other ancient records are like pieces of a vast puzzle. With each new study, they get a slightly clearer picture of what the world once was. But the longevity of clams like Hafrun means they are not solely useful for looking backward. Now that we know they are good for recording the AMOC critically slowing down, that unlocks the potential of these records to provide early warning signals for the future, Ariano Nava said. But again, we'll come to the models in a minute. When you want to go into the future, it's not just extrapolating data, you need models. Because with the models, we're going to change the way we live, energy sources, emissions, policies, human beings, everything, mitigation, adaptation, impacts, everything is going to change the scenario into the future. So the models come into playing a big role, and we have to understand how good the models are to make future projections of a collapse, right? She is now studying that's Beatrice, other clams that, sorry, it must be Maya, other clams that lived across the North Atlantic over the past century and discovered many of the same chemical signals that could be seen in the medieval shells. In unpublished research presented this year at the EGU, European Geological Union's annual conference, she argues that the evidence from the modern clams is an early warning signal that the subpolar gyre is highly unstable and approaching a tipping point once again. This is where the extrapolation happens. That follow-up study has not yet been published in a peer-reviewed journal, but it jibes with the other analysis showing the instability in the region, as well as a recent paper suggesting that the gyre could collapse much faster than the full AMOC, possibly at a lower level of warming. Are these useful, these kind of extrapolations? Of course they are, because they indicate a risk. Then comes the question of how reliable an indicator it is and what we can actually do about them, right? The risks. That doesn't necessarily mean the planet is headed for a repeat of the Little Ice Age, Arellano Nava cautioned. Modern environmental conditions are quite different from those that existed in the 13th century, and it remains to be seen whether chemical signals that heralded a tipping point 800 years ago have the same implications in today's much hotter world. So there is a great interpretation here as well, because we crawled into the Little Ice Age. It's not a big jump, and yet it keeps saying tipping point 800 years ago. This is an interpretation that not everybody agrees with, so you have to be careful. But with the planet now warming faster than ever, Lenton said, there is plenty of reason to curb greenhouse gas pollution. Otherwise, he fears AMOC might pass its tipping point before scientists have enough evidence to be certain about its fate. Well, this is clear that all these should serve as a motivation for climate action, but if you track the pollution and the negotiations and the actions and impact of COVID and so on, you know that such things that are so uncertain can be either easily ignored or they can be misused. So we have to be careful what we are going to use to drive motivation for climate action, right? With all the wars going on and everything, existential crises at shorter time scales tend to dominate. So if you keep saying something may collapse in the future, we have to see how that affects or helps with the climate action. I'm not sure the data will come in time before nature is giving us the answer, he said, and sometimes you know enough to know you have to act. Well, no question that we have to act. Okay, so that's the end of the Washington Post article by Sarah Kaplan. I just wanted to read one paper, that Benyami's paper we mentioned that Sarah refers to, and I'll be very brief about this. Uncertainties too large to predict tipping times of major Earth system components from historical data. This is a very critical interpretation according to me, because the interpretation of the Lenton and Potsdam people is always a little on the other side, saying we are closer than we realize to tipping points. I'm not even sure what that means. Okay, one way to warn of forthcoming critical transitions in the Earth system components is using observations to detect declining system stability, early warnings. It has also been suggested to extrapolate such stability changes into the future and predict tipping times, which is what Lenton and the German groups do. Here we argue that the involved uncertainties are too high to robustly predict tipping times. We raise concerns regarding the modeling assumptions underlying any extrapolation of historical results into the future, the representativeness of individual Earth system component time series, and the impact of uncertainties and pre-processing of used observational datasets, with focus on non-stationary observational coverage and gap filling. So basically that means we need observations to say what are the early warnings and tipping points in the system, and see what's happening now in terms of monitoring early warnings. We explore these uncertainties in general and specifically, for the example of the Atlantic Meridional overturning circulation. We argue that even under the assumption that a given Earth system component has an approaching tipping point, the uncertainties are too large to reliably estimate tipping times by extrapolating historical information. That's the main point you want to take out of this, and I will add some details here. The range of tipping times, without going into details, two products for SST, and third one, well, actually there are some model simulations and some extrapolations of data. So tipping times estimated using DD23's MLE method. So I won't go into the detail. The best estimates of the tipping time is calculated for, there is a method they use for doing this. And basically the point I would stress here is that there are uncertainties. There are multiple data sets used, and you can see the range from very short to very, very long, like 5,000 years. So what do you do with it as a politician, as a decision maker, as a scientist? Do you say uncertainty is just too large so we ignore it, or you say the risk is, potential risk is real and do something about it? And if so, what can you do about it? What are the resources that are needed to do anything about it, and so on, right? The modeling assumptions. So what are the uncertainties that this paper reports? The modeling assumptions underlying the methods for tipping time estimation themselves are largely uncertain. The viability of extrapolating fast forcing trends into the future. We talked about going out of the medieval warming into the little ice age by, changes in the circulation, then volcanoes, then sunspots. So what will come next? We are not always sure, other than sunspots have a short 11-year cycle. Volcanoes are not predictable, and so on. The reliability of using indirect fingerprints to predict tipping times of climate tipping elements is always uncertain. The uncertainties that arise from the bias and pre-processing of in observational data sets with measurement uncertainties and gaps. So as we go back in time, the CLAM data is great, annual data point for 1400 years, but everything else you are using is not so complete in terms of the observational data set. So there are serious issues. Observations are observations, but doesn't mean they give you global information or continuous information, and there is always interpretation involved in them. Okay, so let's conclude with this last paragraph from the discussion of Benyami's paper. In conclusion, we showed that the uncertainties discussed in this work are too large to allow for reliable estimates of the tipping time of major Earth system tipping elements, including the AMOC, the polar ice sheets, or tropical rainforests. These are all counted as tipping elements, tipping points by Tim Lenton and the people who do this tipping point business. And this is based on, if we try to do these based on extrapolating results from historical data, then reliable estimates are just not possible. We emphasize that these uncertainties originating from underlying modeling or mechanistic assumptions, as well as from the used empirical data, need to be taken into account and propagated thoroughly before attempting to estimate a future tipping time of any potential Earth system tipping element. Not just AMOC, but all these other things as well. So again, my main point or motivation for including these is that these attract a lot of attention, press loves it, and climate change is a perpetual newsmaker, and even among media, there are some that like alarmist tilt to their message, imminent collapse of AMOC, into extrapolating from what the paper might have said. Or there are some who are completely cynical. You don't want to be climate denier, but you want to be scientifically robust in taking the message to the public. And we are often a little lax. Are we getting into and justifies the means kind of approach for reporting science results? Well, some people argue that we are. And what is the impact of that? If we lose credibility, then what happens? Or if things don't, if somebody says AMOC could collapse in 2025, and if it doesn't, what happens? Or if we say we are going to exceed 1.5 degrees C, which we pretty much did now, 23, 24, but when are we going back? How long will we have to stay above 1.5 to have any real impact that's different from what's already happening? 23, 24 have been full of climate extremes and impacts, floods, droughts, wildfires, cyclones, etc. But many forecasts have also gone wrong. So if we cannot say what's happening now, next few days, next season, next few years, then why do we want to keep throwing up more of these what may happen, what could happen, and so on, with so many uncertainties? So these are philosophical questions that get raised because this science is trying to inform decisions, and with limited resources and with people still split on climate change as an important issue or not, you have to be careful from the science side not to think that will lose credibility. And Trump is the new president in the US, and you don't know what he will do, right? Because he is motivated by multiple things. He generally denies climate change, but he's a businessman, so if renewable energies can bring money, he will do that. So how climate action will come around, now Putin is again threatening to cut off gas supply to Europe because there is a Ukrainian pipeline that may shut down because the agreement ended or something. I've discussed this elsewhere, because if in the winter gas is not coming from Russia, Europe will buy from Norway and US as it did before, or it will start to burn more fossil fuels that are higher emissions than gas, right? So Europe called natural gas as a low emission fossil fuel, which is fancy footwork because we want to get out of this fossil fuel business altogether. So a lot of things keep driving climate action. Do we need such uncertain things at alarmist pitch to be used as motivation, or will they just hurt the actions in some way? So all these are important points. I'm not trying to make a case one way or the other. I'm just trying to present science and my own views on why we have to be careful about how we present uncertain information. Okay, let's leave this here. Enough preaching.